Which algorithm do you use for your retention project? Probably your answer is easy. But what if your dataset is dominated by categorical features and imbalanced classes? In this video, we're going to compare two models, Random Forest and XGBoost, and dive directly into the code of a freshman retention project. I'm going to show you step by step how we build both models and explain the deep structural reasons why XGBoost thoroughly outperforms Random Forest on categorical datasets. Let's look at the data. We are loading a tracking sheet of first-time in-college students, and our target variable is enrolled spring. It includes the values whether the students stayed or dropped out. Our features are almost entirely categorical or discrete indicators. We have probation, yes or no. We have housing, whether they lived on campus or off campus. And the variable worked answers the question whether they hold a job or not. We map these string columns like retained and worked into 0 and 1 binary flags. If you look at the distribution of student retention dataset, we have over 600 students who were retained and only 153 were not. This is a classic imbalanced dataset. Before we move on to modeling, we check whether we have null values. For the column high school GPA, those two missing values, we just calculate the median value of the whole dataset and fill the missing two rows with that median. To explore the data further, we are calculating the correlation of each variable. We have a negative correlation between high school GPA and probation, which means if we have the values for probation 0 or 1, the highest value, which is 1, negatively correlates with the lower GPA. If the student has lower GPA, he or she tends to be on probation. Then we check the correlation of all columns, specifically with the target variable, enrolled spring. The highest correlation with the target variable is probation. We have minus 0.26. Next one, even though it's positive, but high school GPA, and so on. Let's move on to Random Forest. We divide the dataset into features and the target. We split the data into training and testing sets. We have 20% of our test dataset and 80% will be our training dataset. And we instantiate our Random Forest classifier. We train the model and do some predictions. In order to see how good or how bad our model is, we print out the classification report and we look at the feature importance. Random Forest works by building hundreds of independent decision trees. Each tree is trained on a random bootstrap sample of data, and features are selected randomly at each split. It outputs an average prediction. The model's accuracy is 74%. Since the data is highly imbalanced, we tend to look at the F1 score and the recall. The model thinks that the high school GPA is the most important out of all the features it has. While Random Forest is highly robust against overfitting, it treats every tree as an independent voter. When dealing with complex interaction boundaries between binary categorical features, or when one class heavily dominates the other, Random Forest struggles to target the rare minority cases effectively because it doesn't learn from its previous mistakes. It simply averages the results of 100 brute force structural splits. The high school GPA feature is continuous feature. It's the only feature that is not categorical, while all others are categorical features. The Random Forest calculates importance by looking at how many times a feature is used to split the data. Because high school GPA has dozens of unique values, the Random Forest can use it over and over again to make tiny microsplits. Probation can only be split exactly once, because its values are either 0 or 1. Since the dataset imbalanced, we look at the precision recall curve and the area under the curve matrix. So why XGBoost model is better than Random Forest in this case? Instead of building massive independent trees all at once, XGBoost builds trees sequentially. Each new tree is specifically trained to correct the errors made by the previous trees. The procedure to build a model is very similar, we separate features X and target Y. We split the dataset the same as for the random forest. 20% we have test size and 80% will be our training dataset. To evaluate the results, we also print out the classification report and the feature importance metrics. If you look at the accuracy, it's 0.73, which is, I think, more or less the same what random forest does. But if you look at the F1 score, recall and precision, it is significantly better than the random forest. If you look at the XGBoost feature importance, this model thinks that the most important feature in this dataset is probation, while the high school GPA is at the lowest level. XGBoost by default measures importance using a metric called gain. It doesn't care how many times a feature is used, it only cares about how much the prediction improved when the feature was used. Each time this model makes a decision, it learns, and next time it makes a better decision. Let's look at the precision recall curve, and even here we see a slightly different result. We have 0.91, almost 92. The takeaway is clear. If your engineering workflow involves tabular data packed with binary switches, sparse categories, and class imbalances, don't just rely on a baseline random forest average. Try boosting. XGBoost sequential learning mechanism and penalty structures make it structurally superior for handling categorical data cleanly. If you found this helpful, hit that like button, subscribe for more data science projects, and I'll see you in the next video.